Okay, I hope everybody can hear me. I imagine those in the room can, and I think those on Zoom can also hear me. So welcome to the third in the series of talks that we're giving, sponsored by Climate Reality Project, Silicon Valley, and by the Sierra Club, also the local chapter of the Sierra Club. It is my pleasure this evening to introduce, and I'll probably pronounce this wrongly, but Sudhanshu Jain.
That's right.
Known to most of us as Suds.
That's right.
Suds trained as an electrical engineer at MIT, where he received his bachelor's and master's degree. He then worked for several Silicon Valley companies designing chips for networks and communication. In 2008, he retired from Broadcom Corporation. Is
this sound? No, it's coming out of there.
It's coming out of the mic.
There.
But is this
Okay,
sound on?
we have an echo.
This is off.
I'll keep
It's off.
going for a moment or two to just live with it. Those of us in the room can hear an echo. So after he left Broadcom, he began volunteering at local schools to teach robotics and mathematics and climate change. He served on the planning commission of the city of Santa Clara, and in 2020 was elected to the city council, where he advocated for climate policy, including decarbonization and divestment. While he was on the board of Clara, he met Armand Neukermans, the founder of Marine Cloud Brightening project. He quickly joined that team, a team of retired volunteers and engineers and scientists. And this evening, that's what he's going to tell us about. So this is about Marine Cloud Brightening. Please welcome Suds Jain.
Thank you very much. Can people hear me out there? Okay, I'm going to assume that people can hear me.
Yes, we can.
Very good. Okay. There's an echo in the room, which is disconcerting. It's coming from that computer. We need to get the sound off of that computer.
That's because you have two microphones on. Gary Latshaw should shut his off.
Okay, is that okay, we got it. Now can everyone hear me? Okay, I guess I'm going to assume that you can.
We can hear you. We can hear you.
Perfect. Okay, yeah. All right. So I've been working on this project, Marine Cloud Brightening, since 2012. And I'm working with a bunch of retired engineers, very brilliant engineers. There's Gary Cooper, who's on this call, Jack Foster, who unfortunately passed away last year, me, Lee Galbraith, Armand Neukermans, Rob Ormond, and Jordy Zaplak. And I think the average age of the group is probably 75, maybe. I'm the young one. Anyway, so I'd like to explain what Marine Cloud Brightening is, how it works, why we're even interested in doing this. Okay, Gary, how do I advance this? I need the clicker.
This should do it. No?
No, well, maybe I need to click on this thing. Okay, okay. All right. So what I'm going to talk about is sort of recent events in climate science, why it's urgent that we have to do the research on this. And none of us on this team are advocating for deployment right now. It's sort of a insurance policy. It does not solve the problem of ocean acidification. We're not taking carbon dioxide out of the air. We're just reflecting sunlight back into space to cool the planet, to mitigate the effects of the extra heat that's amping up the hydrological cycle and the weather cycle. There's different types of ways to do this. It's called solar radiation management. Ours is Marine Cloud Brightening. There's another way, which is stratospheric aerosols. We're going to talk about our experimental work and then ask for your ideas. Okay. So if you know the latest IPCC the assessment report 6, which was released March of this year, and it says it's bad. All right. Scientists deliver final warning on the climate crisis. Act now or it's too late. And the fundamental problem is that we've released all the CO2 in the atmosphere, and that atmosphere can take several thousand, that CO2 can take several thousand years to be removed. And every molecule of CO2 in the air continues to absorb heat for those thousands of years. So what we've put up there will continue to heat the planet. So we're at 1.2 degrees Celsius now, but just what we've put up there will get us past 1.5 degrees over time. So I'm having trouble. Okay, here we go. Okay, so to put this in scale, we're emitting about 40 to 50 gigatons of CO2 in the atmosphere. That's equivalent to burning all the forests in Africa every year. So when we talk about tree planting isn't going to cut it because we can't plant that many trees. So that's the scale of the problem. So, okay, I think we're using mine.
That's what you're doing.
Yeah, it works. Okay, very good. Okay. So we've been doing geoengineering actually for thousands of years. Some people say that the temperature of the planet varies over time, but we've been in a sort of a steady temperature for a few thousand years. And some people are saying that it's because people have been burning forests, like the Native Americans used to burn the forest to create open spaces. And they had an intentional program to do that. And so putting that CO2 in the atmosphere could have stabilized the planet from a cooling trend. Okay, but we've done other kinds of geoengineering. If you just look at the Three Gorges Dam, it's 175 feet above sea level. And it stores 42 billion tons of water. That actually slows the Earth's rotation by 60 nanoseconds. It's not a lot, but that's geoengineering, okay? The deforestation changes rain patterns, the air pollution, the unintentional burning of coal has put sulfates in the air, and that actually reflects sunlight. So that actually cools the Earth. Now what we're doing is we've stopped burning a lot of coal. We're cleaning up the diesel, taking sulfur out of diesel. So we're not putting those aerosols in, and that may actually bump the warming because we don't have those aerosols that are reflecting the energy back into space. Already our CO2 emissions are re-engineering the climate. So those are unintentional geoengineering projects, but then we could do something as radical as putting mirrors in space to block sunlight, reflect the sunlight back. We can create machines to suck the CO2 out of the air. There's a concept of taking basalt rocks and crushing them and spreading them over land areas that would then sequester carbon. But you'd have to crush a lot of rock. You'd have to crush 3 tons of basalt to sequester 1 ton of CO2. So those are intentional geoengineering techniques. I'm going to talk about a couple of other ones. And a lot of people are opposed to intentional geoengineering, but we've already been doing unintentional geoengineering. Okay, here's an example of saving glaciers. In alpine regions, they're actually spreading reflective cloth over the glaciers to try to protect them. It's a crazy idea. So as I said, if you burn something, you release CO2. And let's say you have a lump of coal and you're burning that to create heat. You're going to get a certain amount of heat from that lump of coal. But the CO2 that you've released will actually be trapping heat for several thousand years. And the amount of heat trapped is 100,000 times the heat that you originally got from burning that lump of coal. So it's a tremendous multiplier. Okay. So as I said, we have been burning coal. We've been putting sulfates in the air. And those sulfates have, and we'll talk about this, they're cloud condensation nuclei. They're creating making clouds brighter. And that has created a cooling effect of between 0.5 degree and 1.5 degrees. If you look at the contributors to radiative forcing, you have CO2, which is contributing 1.68 watts per square meter. And then you have methane, which is 0.97. And here are error bars for how, and this is our confidence level of how confident we are of these numbers. So you have very high confidence, medium confidence, low confidence. So the thing to point out here is look at the error bars for aerosols. They're massive. So we really don't understand how aerosols interact with clouds and contribute to radiative forcing. But these are actually negative. These here are all positive contributors, and then these here are negative contributors. One is the sun is cooling down a little bit. So, so in terms of intentional techniques to cool the earth, one of the most popular ones that you've probably heard of is stratospheric aerosols. Every time we have a major volcano, the earth cools for a couple of years because these volcanoes emit millions of tons of sulfur into the stratosphere. And when those crystallize, they scatter sunlight back into space. Another way is we have these cirrus clouds that are between 6 and 13 kilometers, and they reflect heat back into our atmosphere, back down to Earth. The technique that I'm going to, sorry, Gary, I don't know how to go back. Oh, here we go. Okay. The technique that I'm going to talk about is marine cloud brightening. So we have these low level clouds up to 3 kilometers, 3,000 meters, where we have plenty of moisture, but we're not forming clouds because the clouds form over condensation nuclei. You have hygroscopic particles. It could be sulfates or it could be salt crystals, which are naturally forming. And they create these cloud condensation nuclei that will then create droplets. So I'm going to talk about the two major forms of solar radiation management. One is stratospheric aerosols. So there's a team at Harvard that's looking at a technique to spread aerosols in the stratosphere. Originally, they were looking at sulfur because that's what volcanoes do naturally. But it turns out that the sulfur can negatively impact ozone. It can destroy ozone to some extent. So it's not the greatest technique to put sulfur up there. It's what volcanoes do. So they're looking at other particles, including diamonds. Powdered diamonds is one way to scatter the sunlight. The other technique is marine cloud brightening, which is the technique we're working on, which is to spray seawater or salt water into very, very small droplets that evaporate and create these crystals that will then drift up and become cloud condensation nuclei. So the hard part of this is that the droplets or the crystals have to be just the right size. If they're too small, the droplets won't be big enough to scatter sunlight. If they're too large, they'll actually grab all the moisture out of the clouds and they'll rain out. And you'll lose all the humidity. So the ideal size is between 20 and 400 nanometers. So they're very, very small and they have to be monodispersed. They have to be essentially all the same size. If you put aerosols in the stratosphere, they last about 2 years. So the downside of that is if you got it wrong, if you put up too much, then you could have other effects. And I'll talk about some of the negative effects of putting a lot of sulfur in the stratosphere. We've had famines created from volcanoes. The marine cloud brightening has the advantage of the particles only last about a week. So if you didn't get it right, you could just turn it off and the problem, whatever problem you're creating would be gone. The problem with stratospheric aerosols, when you do modeling, there are certain parts of the planet where you change the precipitation levels. So you could create lower precipitation in parts of the world, droughts, and you could create big rain events in other parts. So the modeling is very critical for where you put the aerosols in the stratosphere. The National Academies of Sciences has taken this on seriously. They've created a number of reports. And here's, I'll just quote two paragraphs from this. The creation of this study committee is one response to the need for understanding the full range of options for dealing with the climate crisis. Solar geoengineering research to date is ad hoc and fragmented, with substantial knowledge gaps and uncertainties in many critical areas. So the funding has been controversial because you're talking about weather modification, and that could be weaponized. So people don't like the idea of messing with the climate. You could have unintended consequences. As I've mentioned, we don't like this technique, but we figure that there's so little that we understand about aerosol cloud interactions and how this all works. We have a lot of computer models, but you always have to validate your computer models with field experiments, with real world experiments. So we feel that we need to be working on this. Our team has been working on this for 14 years, and we still don't have not perfected our sprayer. So it takes a long time to do the research. And if we wait another 15 years, it might be kind of too late to start a research project. So, so here's an example from Mount Pinatubo. The Mount Pinatubo erupted in 1991, and the global temperature dropped by 0.5 degrees Celsius for 2 years. Okay, we actually can look at proxy data, and we can look at temperature drops from other volcanoes. We have this is a chart of temperature rise over time, and you can see here that when we had the Mount Agung volcano, we had a temperature drop. And then we had the El Chichon volcano, we had a temperature drop. Pinatubo had a temperature drop. And this is just a simulation of what would happen as if we had another Agung eruption today. So Pinatubo injected 17 million tons of sulfur dioxide in the stratosphere. So so you can see that that was twice as much as the El Chinchon. And so you can see that the drop was larger than the El Chichon volcano. This is an interesting, sorry, I'm having trouble with this. It's not my computer, it's Gary's computer. So, all right. So there, in 1816, we had the summer, the year without a summer, okay? What happened was we had two major eruptions, one in 1810 AD and one in 1815 AD. And this, in 1815, it was Mount Tambora. And what they say is the Berkshire Hills of Massachusetts had frost on August 23rd. There were famines in China. There was an agricultural disaster in New England. So you can see the impact of this cooling, and it was only about 1 degree Celsius, but it had that big an impact. So we have historical experience showing that this would work. This would cool the planet. But the issue is, when do you spray? It would take thousands of aircraft going up into the stratosphere to spray our preferred material is calcium carbonate, calcite. It does not impact ozone. And our team has actually helped work on a sprayer that would spray calcium carbonate particles up in the stratosphere. So for stratospheric aerosols, for calcium carbonate, they're sort of predicting that they would put 1 to 2 million tons per year in the stratosphere. And it's very feasible technology. The cost is pretty modest. And it's very doable. The disadvantages are it's very difficult to sell something this radical to the public, even though the burning of coal and the diesel has already emitted far more sulfur into the atmosphere than we're proposing at this point. And then the other problem is it's very hard to do an experiment because if you wanted to put just a few hundred kilograms up in the stratosphere, it disperses so quickly that you could not get a signal. It wouldn't be big enough to create a signal that you could detect to see how well it worked. So you kind of would have to do it at a massive scale. And the smaller amount of particles, it takes longer to look at that signal. You have to look at it for a longer amount of time. If you put up a massive amount of particles, you'd get an immediate response. So again, if you got it wrong, those particles would settle out in about 2 years. If you use sulfur, you could deplete the ozone layer. And then, as I said, the effects of this are not uniform over the planet. So some parts of the planet could have less precipitation, droughts, so on. So here's a prediction by the Harvard team, David Keith. So they're looking at they have 3 different scenarios, putting 3 million tons of sulfur dioxide in the Arctic stratosphere, 5 million tons of sulfur dioxide in the tropical stratosphere, and 10 million tons in the tropical stratosphere. So here you can see with 10 million tons, you have a very large drop in temperature for 2 years. Well, this is you're doing it every year over a long period of time. So this is over 10 years, you'd see this drop in temperature. Okay. So it turns out that the Harvard group had this project called SCOPE-X, which is the Stratospheric Controlled Perturbation Experiment. And what they were going to do was they were going to send a balloon up into the stratosphere and they were going to spray particles, just a kilogram of particles. And then they were going to fly this balloon, it's a controlled balloon, through the plume and measure particles to see how the particles disperse. And they'd been developing this for years and years. They were going to do it in Finland, but actually in Sweden, but the native people in Finland blocked the project. And their reasoning was, you're opening the door to something more massive. So you're starting down this path of doing this experiment. So the Harvard group was then changed it so they weren't going to spray anything. They were just going to fly the balloon up there to see if they could steer the balloon and test out all their equipment. That got blocked too. So this is kind of what we're up against. Our team got money from Bill Gates years ago, and when we first started, about $300,000. But then a reporter, and we were based in Sunnyvale, a reporter from England got hold of the story and said that some rogue scientists were working on this experiment with Bill Gates money, and it got some bad press for that. So Marine Cloud Brightening is the project that I'm working on with my colleagues, Gary Cooper and Armand Neukermans, Lee Galbraith. This was actually conceived by John Latham in 1990 that you could spray these particles up there. It's based on this Twomey effect, which is that here, if you have a cloud with a small number of particles, you have a low albedo. That means a low level of reflection of sunlight. But if you introduce a lot of cloud condensation nuclei, you can distribute the water in these large particles into lots of small particles, and you would increase the albedo. And this next slide here shows you how you can affect the albedo based on the number of particles. So if you had 50 particles per cubic centimeter, then you'd get a reflectivity of 0.2. But if you had 1,500, you could actually get almost a perfect reflectivity, almost a reflectivity of 1. So depending on the concentration of nuclei. And here's another example of the Twomey effect, where it's not very clear in this picture, but here you have glass beads. And so here the glass beads are larger, so it looks gray. But if you were to powder them into a very fine powder, it gets bright white, like sugar or salt is bright white because it's scattering a lot of energy. So this is the basic philosophy by what we're trying to do. And there are large parts of the ocean, especially on the west coasts of continents, where there aren't a lot of cloud condensation nuclei, but in these marine clouds, these stratocumulus clouds, there's plenty of moisture, but there just isn't the nuclei. And part of it is that the wind comes over the Pacific Ocean. By the time it gets to the coast of California, it's basically clean a lot of particles. These here's some modeling. Okay, so the experiment that shows that this would work is that cargo ships burn bunker fuel. And bunker fuel used to be up to 5% sulfur. It was the crappiest fuel. It just had all this junk in it. And so from satellites, you can observe these ship tracks. So these are ships that are crossing the ocean, and you're creating clouds from the sulfur from their smokestacks. So this shows that if you emit these particles, you can actually brighten clouds or create clouds. So this is the basis of what we're trying to do, is if we can intentionally introduce, and we have 50,000 cargo ships that crisscross the ocean. So if we put these sprayers on these cargo ships and we paid the cargo companies, it's like carbon offsets. If you pay them to spray at just the right time when the conditions are right, you could create these clouds and offset the warming effect. So the problem is that we've changed the laws on this. So we've gotten this unintentional cooling from all the sulfur being emitted, but since 2020, now in the open ocean, the sulfur content can only be 0.1%. So it's dropped by a factor of 50 in terms of what we can emit, which is a good thing, because actually, if you look at all that sulfur, it's caused an incredible amount of death and disease. They estimate that the shipping industry alone was estimated to cost 400,000 premature deaths a year from lung and cardiovascular disease. So there's a good motivation for cleaning up this sulfur, but it's not helping our radiative forcing budget. Okay, so here's some modeling that's been done. So if you were to apply marine cloud brightening to about 10 to 30% of marine clouds, you could possibly offset the doubling of CO2. So pre-industrial, we were at about 290 parts per million. Now we're at 420 parts per million. So doubling would be 580. So we're getting there. So if you look at this, this looks at the cooling that you would get for covering 5% of the ocean surface area with spraying, okay? And you'd have, you could double the CO2, you could offset the doubling of CO2 if you increase droplet concentrations by 120%. And that would decrease the cloud droplet sizes by 40%. And you'd get a 12% increase in cloud cover. So you can see the planet has gotten quite a bit cooler, and the effects are not uniform. So that is one of the problems, is where and when do you spray? So now I'm going to talk about our journey through developing a sprayer. So John Latham had originally proposed this idea in 1990. And so there's been a lot of modeling. The question is, can we create the monodisperse spray? So they had a conference in 2008, sponsored by Bill Gates Group, Pfizer. And they asked to start a innovative project in Silicon Valley. And so far it's been mostly a volunteer effort. So I want to talk about Armand. Armand asked me to take this slide out, but I have to talk about Armand. The guy is incredible, you know. He's 80 years old and he still works every day on this project. He reads papers, comes up with incredible ideas, and he has been mostly funding this project from his own pocket for the 14 years this project has been running. So he's assembled this geriatric team that he knows, and he knows practically everyone in the valley. So once we needed holes drilled in a diamond sheet so that we could create nozzles made out of diamond, because the salt water is corrosive. And so he knew this guy, and he traded him 2 boxes of Costco biscotti for drilling holes in our diamond. So Armand, I have to talk about Armand. He he sold his company to Nortel in 2020. He was named Silicon Valley Inventor of the Year in 2001. He's from Belgium. So he was knighted as Officer in the Order of Leopold by the Belgian Crown. And the key thing was that he had worked at HP and Xerox, and he worked on inkjet printers and toner. So he was really good at making monodisperse, very, very precise particles. And so he was basically recruited by the team to lead this effort. So, so they invited him to Edinburgh, Scotland, and basically, you know, pointed at him and said, "You're going to do this." So he agreed, and he's an incredible guy. You know, I met him at a fundraiser and he said, "Come by the lab and take a look at what we're doing." And I haven't left. So, all right. So what is our goal for this project? And it's to create a sprayer that will create 10 to the 15 nuclei per second. They have to be very precise sizes. And the size is actually still not very well understood. Ideally, we want it to be between 40 and 80 nanometers of the dry salt crystals, but the modelers have said that the range could be anywhere from 20 to 400 nanometers. So we're going to try to do some field experiments and figure out what the right sizes are. The other thing that complicates it is that when these particles are out there, they coalesce. So the salt particles will join together, coalesce, and you'll get larger particles. So we spray into a tent and we watch the evolution of the particles, and we can see that the size distribution increases. The mode increases. All right. So this is the example of one of our sprayers. This is a effervescent spray where we combine salt water and air, and we spray through a 125 micron nozzle. And it's 3.2% salt, which is seawater salinity. It's 84 atmospheres. And you can see that that our distribution is pretty, pretty tight. This here is 10 nanometers. and this here is 1 micron. So you can see that it's very, very tightly and centered around 80 nanometers. So, so we've come close to doing what we want to do. We're in this nozzle, we're creating about 3 trillion particles. So we'd need 300 nozzles to get to our 10 to the 15. So, so I'm going to go through the different techniques we tried. The first thing we tried, this was before I joined the team, was we just had a very, very small orifice that we would spray through. And this is modeled after what they did to create Xerox toner. It was actually 96% monodisperse, and they just sprayed through a very fine orifice. And so the problem is that when we tried this, we had to spray through a 0.5 micron hole. And the problem is that we had a whole filtration system, and it as hard as we tried to filter the water, there was enough junk in the water and materials precipitating out of our equipment that would then clog the holes. So we could just not keep the holes clear. So we had to abandon this technique because it was just not practical. The next thing we tried was Taylor cones, which is where if you have a, this is actually a felt pen here. And if you put a plate here with a high voltage on it, you can actually draw a stream of particles out. And this actually shows you the particles coming out of here. And you create, the problem is you only create 10 to the 8 particles per second per jet. And you can do this with a felt pen or just a hole, a capillary. But you need 10 to the 15 particles, so you need 10 million jets. So it's complicated for how you would build that. And obviously you'd have to use some sort of lithographic technique to do that. The other problem is that when the particles come out, they're highly charged. So they would then see the image charge in the ocean when you're spraying, and they would drop down. So that's problematic when they're highly charged like that. So one technique we used to measure the product of these Taylor cones is we would spray them, and then we'd have a silicon wafer that we would electrostatically precipitate onto the silicon wafer, these particles. And then this is an SEM image where you could see the sizes of these particles. And you could see that they were very monodisperse, again, centered around 80, 90 nanometers here. So it would be a great technique. We just didn't have the capability of doing all the lithography to get that right. So we abandoned that, and then we moved on to supercritical saltwater spray. So the idea is if you have if you're trying to spray through an orifice, you have the surface tension that makes it difficult. You need a lot of energy to spray through that. But if you can get to supercritical, you lose all the surface tension. There's no, it acts like a gas. So then you can spray through small nozzles very finely. And what we discovered is the salt mostly stays in solution. So you can spray through this. What we discovered actually, and here's some sprays, and I hope the audience can see these colors, but when you see, we just have white light flashlights pointing at this. When it turns blue like this, you know that you have smaller particles because you're scattering the blue light through the smaller particles. And so this technique, what we had was we had a tube going through a block, an aluminum block, serpentining through here. We had heaters in this block, and then we would spray out. What we discovered was that salt water at these temperatures and pressures is incredibly corrosive. So when we had titanium tubes, there's iron impurities in the titanium tubes, and the iron was leaching out and clogging our nozzles. So So then we ended up gold coating our tubes and that sort of worked for a while, but we discovered that the amount of energy that you have to put in to this just makes it not practical. So heating up the water to those temperatures and pressures is impractical. So we abandoned that. So it worked, salt water was very corrosive. It requires about 350 kilowatts of power to create 10 to the 15 particles per second. Most of that's thermal energy. And so it turns out, cargo ships have a lot of power because when they're burning all that diesel, they're wasting a lot of heat in their power plants. A typical engine's like 30% efficient. So you have all this heat that we could harvest to create some of this heat. So having the cargo ships provide this power isn't too much of a burden, but just the ability of working with that corrosive material. We abandoned that, and then we moved on to effervescent spraying, which is spraying salt water and air together. So you can do it two ways. You can have this is the gas going through the center and the water coming from the sides, or you can have it the reverse. You can have the water on the inside and the gas on the outside. So our preferred method is to have the liquid on the outside. What we do is so when you spray through with the liquid on the outside and the air on the inside, you create these thin sheets, and this is choked flow here. So it explodes when it gets out into the atmosphere, and it creates these little droplets. So you create these thin sheets that then explode into tiny droplets. The way that we do it is actually, we have a cone-shaped nozzle, and we spray the water tangentially on the outside, and the air goes through the middle. And so what happens is as the water creates this annulus on the sprayer, and as it goes down narrower and narrower, it spins faster and faster. It's like a ice skater pulling in her arms. She goes faster and faster. So when you tighten up the radius through this cone, it spins faster and it thins out the liquid. So so that's the technique that we've done. This is a picture of our spray. It's 3 trillion droplets per second. And so you need 300 of these nozzles to get 10 to the 15. What we've discovered is measuring particles this small, because these are far smaller than what you can see with your eyes. So if we were actually to spray at just the right size, the dry particles, you couldn't see them. You wouldn't see them in the air. So you need to have very sophisticated equipment to be able to measure particles down to 10, 20 nanometers. So there are two different pieces of equipment used. We use a scanning mobility particle sizer, SMPS, and an aerodynamic particle sizer. The SMPS will measure from 10 nanometers to about 700 nanometers, and then or 2 nanometers to 700 nanometers, and then the aerodynamic will go 500 nanometers to 2 microns. So you have to have the combination of the two. One of the things that we want to be careful is that we're not creating large particles, because the large particles will then grab all the moisture out of the clouds and rain out. So we lose all the moisture. And what we want to do is prevent rain. We want to make these clouds last longer, have them be brighter, smaller droplets, and they scatter more light. So our idea is to reduce precipitation through this technique. Again, this is the distribution that we got from this nozzle. One of the things that we So here you can look at the number of nuclei created. And you can see how it drops off here. And then this is the mode here. And in this case, the mode is like 40, 50 nanometers. So what we see here is about 98% of the nuclei are in the right size, 40 to 400 nanometers. The problem is that if you look at the mass distribution, the mass is all in the large particles. So all the energy you're putting in is going to particles that you don't want. And you really have to be very careful that you limit the number of large particles. And that's what we're struggling with now, is how to limit the number of large particles. What we decided was that we have these snowmakers that essentially do what we're doing. They use effervescent spraying, they use air and water, and they have a fan through the middle here that blows air out. These outside ring are effervescent nozzles. The inside, the ones deeper into the sprayer are just water spray. And you can see the results of that when they use these nozzles to create snow, artificial snow. So that was our idea. We have not done any, we've only done experiments indoors. There's a group in Australia that's very concerned about saving the Great Barrier Reef. The Great Barrier Reef is about a $6 billion tourism industry for Australia. So it's very important that they preserve that. You've probably heard of the bleaching events. Bleaching is due to ocean temperatures. There's a symbiotic relationship between the algae and the coral animal. And when it gets too hot, the algae start creating radicals that annoy the coral, and then the coral ejects the algae, and then they starve to death because they don't have any photosynthesis. So what we notice is when it's in the northern part of the Great Barrier Reef, it's warmer, and that part is 99% bleached. In the middle third, it's about 50% bleached. And then in the bottom third, it's about 10% bleached. So the idea is to cool the ocean temperatures. The Great Barrier Reef is a harder problem because they don't have marine clouds. So they're thinking about spraying larger particles that then in themselves would scatter light without having to absorb moisture and create droplets. The other challenge is the Great Barrier Reef is thousands of miles long, and it's very narrow. So to spray along the length of it is very complicated. But they're doing field experiments. And one of the questions we had was that if you spray and these droplets are evaporating, they cool. And that cooling would cause the plume to drop. And we were wondering if it would get lifted. And what they've shown in Australia, their ocean temperatures are warmer than what we have here, but the plume rises there. So they're also struggling with how to measure the right particle sizes and scattering. So the last technique that we're currently working on is what's called superheated spraying. And it turns out this idea was originated at Delft University. And the idea was to spray water into the turbine inlets of gas turbines. And you would cool the inlets so that you could get a higher efficiency. And it would actually increase the efficiency up to 15%. And it would reduce nitrous oxides because it's cooler. So the evaporation of the water, you can inject it into these turbine inlets, would then give you all these benefits. And you'd have to inject 10 to the 13 to 10 to the 14 drops per second. The problem is they ended up abandoning this because not all the droplets were small enough. So you would have some larger droplets that would impinge on the turbine blades and crack the turbine blades. So after years and years of working on this, they abandoned it. And the Russians took it on, And so the Russians, this institute in Moscow, has been working on this now for 15 years. And what they discovered was that the nozzle design is very important in creating the right particles. So if you look at this next slide, the original design, which is just a regular orifice nozzle, would give you a bimodal distribution. So you'd have small particles and then you'd have these larger particles. By using a de Laval nozzle, an expanding nozzle, they were able to suppress the second larger mode of large particles. And so then you'd be left with these smaller particles, which is exactly what we want. So we have been working on this probably for about 3 years now to try to create the right nozzle with a superheated. And the way we do this is we have a pressure vessel. We started out with stainless, and we were using the stainless for a while. And then we opened it up after probably about 6 months, and we noticed it was very rusted inside. So we were very concerned that with the superheated, what we do is we have a pressure vessel. We put salt water in there and we heat it up with a heater. And then we have valves that we open up when it gets to be hot enough and high enough pressure. And then we get this huge plume coming out from the nozzle. So when we used a stainless pressure vessel, it got corroded. So now we went to a Hastelloy, which is a nickel-based pressure vessel that is not corroding. So, but they're very expensive. So there is a group that's called the Silver Lining Project. It's based out of University of Washington, and we are affiliated with the University of Washington as well. They're basically our academic sponsor. So when people donate money, they get the tax deduction to help fund some of our work. But as I said, this work is controversial. So Silver Lining has been doing a lot of fundraising, and so far, most of their money has been philanthropic. They have just started getting some government funding, but so far, because of the controversy that we had over the Bill Gates money, and we're depending on Silver Lining. So you can go to their website. They have a great website where they have a bunch of papers. This is one of their papers that they've produced. So in conclusion, clouds and aerosols have a large contribution to radiative forcing, but again, those error bars are massive. So that's what we want to narrow down our certainty and our understanding of cloud aerosol interactions and radiative forcing. Again, the IPCC report paints a very dire and urgent picture that, they're saying we have to get to net zero emissions by 2040. Any of you think that that's actually going to happen? So the idea is, we're looking at this as an insurance policy, that let's do the research, let's figure out how to do this, where to spray it, the right latitudes that you want to spray in, the amounts that you want to spray, so that you don't get droughts or precipitation events. And again, the problem is you're not solving the issue of ocean acidification, because the CO2 is still in the air and it's still dissolving in the oceans and preventing, seashells and animals from building their shells. And then there's the concept of the moral hazard, right? So the oil companies kind of love this idea, because they're like, yeah, we can take care of it. Let's just keep burning because we can handle the heat. We can take care of the heat. So again, as I want to repeat, we've been working on this since 2009, and we don't have the perfect sprayer, and we don't have any field tests to validate our models. So the research takes a long time, and the amount of money being spent on, reducing CO2 and even doing adaptation now with seawalls and other things that we're doing is massive compared to what's being spent on this research. So, so again, like the National Academy said, we need to be working on all options, including this insurance policy. So thank you very much. So do we have any questions?
Thank you.
Okay. Couple on Zoom, okay. Okay. Okay.
You want to explain the Zooms?
Okay, I can do somebody.
Explain what?
You said there were some Zooms?
There's some in the chat room.
Oh, in the chat. Okay, let me go to the chat. All right.
Anybody in the audience while he's doing that? Any questions from? Anybody
Okay.
here?
You got it? Okay.
Yeah, all right. So Karen asked, oh, so Karen asked, how high can cloud albedo be pushed to maximize the brightening impact without getting negative results? We have no idea, Karen. As I said, if you introduce 1,500 particles per cubic centimeter, you could get the albedo up to 90%. But you know, it's impractical probably because you have atmospheric effects that are going to cause the spreading of these particles. You can't keep them concentrated in one area. They're going to spread. So if you wanted to do that, you'd end up doing, you know, 1,500 parts per cubic centimeter over the whole planet. Right?
Over repeatedly every.
Yeah, and you have to continually spray. Exactly. Yeah, every week. Yeah. The next question was, okay, there's only, I see only two questions.
you here?
One question.
What's that?
Why are you here? This is a meeting just closing.
I'm here
there's
for
somebody.
Sierra. I'm a paid member of Sierra Club.
Okay. Oh, okay. Yeah.
I don't hear any other questions. Please put them in the chat.
The meeting is nearly
Having some
over.
audio problems.
Hmm? Oh, sorry.
Okay.
So. Cover this.
Yeah. Is it on?
Is it coming good? Hello?
I don't hear it.
I can't hear it.
So ask the question and I'll repeat it. Yeah, ask the question, I'll repeat it.
So the question is, so explaining if you have an ideal nozzle.
Yeah.
and spray it, how often would you need to be?
So we would be spraying continuously. Oh, yeah. So the question is, if we had the ideal nozzle, how often and how many sprayers will we need? Because it's 10 to the 15 per ship, but then you have 50,000 ships. So we would actually probably have 5,000 ships spraying kind of continuously around the globe.
But in spraying at ground level is sufficient.
We believe so. And when you spray, you have evaporative cooling. So the question was, you know, spraying at ground level, is that sufficient? So that's a big question for us. And if the cooling effect for particles to drop, we would have to add heat. So maybe we could use the heat from the ship's smokestack to be able to lift the particles up. So we'd have to do the field experiments to really see. In Australia, because their ocean temperatures are higher, they've seen the lifting. So they've seen convection upwards. Yeah, high enough. Yeah. It has to go to about 2,000 or 3,000 feet. Yeah. 2,000 or 3,000 meters. Yeah.
So there's a question on the chat.
Okay. Okay. So the question is, why was the Gates funding controversial? Just like David Keith with his ScopeX project, that was controversial and it was shut down. And all they were going to do was put up a balloon. And there's hobbyists that put up balloons all the time. But it was shut down because it would open Pandora's box. It would open the door to, radical weather modification. So people were concerned about that. I think there's a number of people that would rather not know and then deal with this problem in other ways. But in the case of Bill Gates, was that the article basically said there was a group of rogue scientists working on weather modification and changing the planet. So that
It's a loaded word.
so that was the idea. I think a lot of people around the world don't really like what we're doing here in Silicon Valley with, there's negative consequences to technology. I mean, just look at social media, how destructive that's been, and what's going to happen with Chat GPT. There's a lot of things. I mean, Italy has banned Chat GPT. So it's those kinds of controversies that we're dealing with.
I don't know if you can hear, if the audience can hear me.
Yes, I'm going to go through that. Okay. So Anthony Strawa is asking the question, do you see this tech as an alternative to mitigation? Would this technique work in the Arctic? Tony, this is not an alternative to mitigation. Mitigation is basically reducing our emissions or getting the emissions out of the air. And as I've described, we're not solving the problem of its acidification, which is a serious problem. You could collapse the whole ecosystem of the ocean. So I think what I read somewhere that coral reefs contribute to something like 30% of our aquaculture. So it would be a disaster if we don't take care of our mitigation, plant trees and reduce CO2 emissions from burning fossil fuels. But like I said, we're not going to get to what the IPCC is recommending, which is net zero for all major countries by 2040. I just don't see that happening. So if we continue to burn fossil fuels, all these countries promise that they're going to meet their targets. They always slip their targets. We could be in a world of hurt, and I figure we need an insurance policy. I mean, storms with the extra energy in our hydrological cycle, we're talking about Category 6 hurricanes, and we're talking about, all these tornadoes that are happening. So you're just putting a lot more energy in the system, and we have to somehow reduce that energy, and that could be solar radiation management. Hope that answers your question.
Question on another question in the audience. My question is, they broke armor, we're using calcium carbonate.
Yes.
That is basically what's in shells and limestone, and it's part of the calcium cycle as well as the carbon cycle. What about sodium bicarbonate, which is the baking soda? That is essentially in the ocean. There are sodium ions and there's bicarbonate ions in the ocean, and it's a white powder in a solid form. Are you married to salt? Sodium chloride?
Well, the sodium chloride is what we're using for the Marine Cloud Brightening. We're not proposing any chlorine stratosphere. That would be a disaster.
No.
Yeah.
So it's going to precipitate out. It's still sodium bicarbonate.
Yes. I don't know why the team rejected the Harvard team. They looked at a bunch of materials, and they seem to prefer calcium carbonate. So maybe it's more stable than sodium bicarbonate. maybe we don't want to put
The
sodium up there.
bicarbonate is a buffering agent, so it would lower it would raise the pH of,
Right, but the amount of sulfur that they're proposing to put in the stratosphere is minuscule compared to what we're already emitting from burning coal. Oh, okay. So the question is that sodium bicarbonate is a buffering agent. So when it precipitates down to ground level, it could reduce acidification. So the amount that they're proposing would probably have a minuscule effect. Right now, if they were to spray sulfur up there, it probably wouldn't change the pH very much more than what the pH is already, because it's minuscule compared to the amount of the CO2 dissolves into the ocean that acidifies it, but also the sulfur from the burning of coal also acidifies the oceans and that's why we had all of the dead forests when we were emitting lots of sulfur. So
There's another online question.
oh. How does this compare to sunshades in orbit proposed to reduce solar intensity? So that again is extremely expensive. People are looking at putting reflectors in the Lagrange point. But every kilogram that you send up into space costs tens of thousands of dollars. So to put solar reflectors out in space is a very expensive proposition. This is far cheaper than that. And so that is the question. So he's saying the price of launches are dropping fast. I haven't looked at the economics of that. I know people are seriously looking at that. That's not what we're working on.
So, yeah, I guess the other question, are there other countries, maybe other countries that have a particular concern, like Australia does?
So the question is, do other countries have concerns? Like, say, India about this work?
Motivation.
Well, if you've read Ministry for the Future, Kim Stanley Robinson's book, India goes ahead and does it, right? So the problem is that the international rules for doing this, you could have, it's fairly inexpensive to put this stuff up in the stratosphere, just a couple $2 billion a year. So you could have a rogue nation that just decides that things are bad enough that they're going to do it, right? So the governance part is a big issue, and the governance part is actually holding back the field experiments. So just like David Keith from Harvard couldn't get permission to fly his.
That was US issue.
That was actually the native people in Finland prevented him from. So originally the Swedish government. Yeah, Australians doing it because it's within their territorial waters, so they're spraying. But for us to spray here in the US is complicated. We don't have permission yet to spray. So we're spraying indoors right now. Okay, we have another question.
What level of low reserve carbon energy would be necessary for this to be net positive in terms of actual temperature reduction?
So it would be net positive almost immediately. I mean, if you think about it, every molecule of CO2, you burn it and you get a certain amount of heat, but you're going to get 100,000 more times as much heat trapped because that molecule is up in the atmosphere, right? So what we find is the multiplication factors of the energy we put in to how much energy is reflected back in the space is in the thousands.
There's also like a key factor, right? Is if we run this continuously burn energy to continue spraying, water molecules into the atmosphere now.
Yeah, so the question is, yes, you're continually having to expend energy to spray. But the idea is that you're continually trapping on the planet due to this carbon dioxide that excess heat, like 70% of that is being stored in the oceans right now. So we have all this excess heat trapped on the planet, but if we can reflect back tremendous amount of that heat, we're not warming the planet. So the amount of CO2 you generate to do the spraying, when you calculate it out, you still get a gain of thousands from the reflectivity of the clouds. Does that make sense?
Okay. 1,000 times more heating reduction compared to effective heat penalty from the energy put in.
Correct, exactly.
And the heat doesn't need to come from burning.
If it's renewable.
Yes, exactly. Yeah.
Any more questions online or?
Is there a question online?
There's another
Okay.
question online.
Do you want permission to spray in the atmosphere, however modest? Are you ready for that? And if you want permission, how can we, the community, help to get permission? Is that possible with some state level legislation? So, the US within our own boundaries could spray, but, we have to go through government agencies. So of course, raising awareness about these techniques, and they're already raised at the highest levels. The National Academies of Sciences is doing work on this. The fundamental problem is that we have a lot of misinformation that spreads around. I mean, people believe in chemtrails, chemtrails. They look at these contrails from airplanes and they think that's the government spreading chemicals that are doing mind control. And then you have, the issues with the COVID treatments, we have a lot of misinformation around. So the idea is we're going to get some pushback from people that think that we're going to destroy the planet, but we need to do the research. We absolutely have to do the research, whether we deploy it or not. We're at this point still not advocating for deployment because we think that we still have a lot of time left the key thing is reduce emissions. And then after that, do some adaptation, but adaptation is very expensive. I mean, building seawalls and barriers is very, very expensive.
Is funding for something like the Sept?
So the total funding in the US, I believe, so far is only like $4 million, which is pittance compared to what we need a year. Yeah. And so it's through DOE, I think. Yeah. And NOAA. So if you look at the people working on this seriously, there's only our team, which is at Palo Alto Research Center, and we're teamed up with the University of Washington. And then there's a group that's just starting in Cambridge University. There's a group in Australia. And as far as I know, those are the only serious efforts working on this. And we're a bunch of old guys. So we really need to, and we do this part-time. So we really need to have, well-funded, full-time people working on this. We do have 2 postdocs at Park that are working on it full-time, but our geriatric crew is, unfortunately, Jack Foster, like I said, dying off. He
From the
passed away
base
last
comes
year.
wisdom.
Yeah.
Are we through with the,
I don't see any more questions.
and any more questions in the room here? Well, if not, let's, thank you for a very stimulating talk, and maybe controversial, but very interesting. Thank you.
Okay, thank you.
Thank you all for coming. So, our memory's not that good. What's our next month?
Next month is,
Is that the cement?
concrete from the air.
Yeah. Yeah. It's a concept in which, the concrete, you may know, is like the construction of the cement, and the concrete is like 6 or 7% of all the carbon dioxide formed. So this is a technique in which the concrete will actually become somewhat negative in terms of carbon dioxide emissions.
Okay.
Could you slow down?
Okay, good job.
Okay.
Very interesting. Well,
I have a couple questions. Campbell, did the recording